The title of chapter 2 is called More on Functions. Because we were introduced in functions in chapter 1. Now we're going to go and just talk about all of them, the rules, properties, how we can use them, what they're used for, and everything. So this is the first one. We're going to talk about increasing, decreasing, and piecewise defined functions. Where's our sheet from chapter 1, or section 1? So first off, let's look at what defines an increasing function. How would you define that increasing function in your own words? How would you know if a function is increasing? Or how would you know if a graph is increasing? Ah, yes. So it's going up like that. That's an increasing function. Right. Very good. Remember, a graph is made up of points. So here we have x1, and that goes to y1. And then we have another point. That's made up of x2, y2. Now, in the x's, it's always going to right. So it's always increasing. So in other words, x2 is always greater than x1. So as x2 is greater than x1, what determines if it's increasing is if y2, the second point, is higher than the first point. Then if y2 is greater than y1, then the function is increasing. Conversely, a decreasing function as x2 is larger than x1, how do we know x2 is larger than x1? Well, now x2 is larger than x1 because it's to the right of it. Because it's to the right. If a number is to the right on the number line, it's bigger than the one on the left. Obviously, yes. But these correspond now to our y1 and y2. If y2 is less than y1, then the function is decreasing. Those are for linear equations. Here's a graph of a function. The function is x squared. The lowest point of the graph is here at 0, 0. Tell me where the function is increasing and where the function is decreasing. And whenever we talk about this, whenever we talk about the where the function is increasing, decreasing, we only refer to the domain, and we use interval notation. So where is it decreasing? Where is the graph going down? So here it goes from negative infinity. So yeah, put your pen here. You're going this way. It starts going down. So it starts going down from negative infinity all the way to 0. And then where does it start going up? Well, at 0 to positive, yeah, at 0 it starts going up. What's happening at 0, 0? What do you mean stays there? All these numbers stay where they are. They can't move. Is it increasing or decreasing? It's constant. Very good. If it's constant, the graph is horizontal. But right here, what's happening here, if this is an arrow, on this side of the graph is going down, going down, going down. When it gets to 0, it's horizontal. It's neither increasing nor decreasing. And then it starts going up. And that's why we never have a bracket where they overlap at the endpoint. All right, let's look at example 1. Here we have a graph. So this point here is at -1, -2. This point here is at 3, -2. This point here is at 5, 2. And that's all I need. Where is the graph increasing? Where is it decreasing? Decreasing. So we have decreasing. So it's going from negative infinity to where? -1. Is there anywhere else? So from +5 to infinity, it's decreasing. Since we have multiple, what do we put between those things? Since we have, the answer could be here or it could be here. It's decreasing at those places. Where is it increasing? Yeah, it starts at +3 and it goes to 5. That's where the graph is going up. Remember, we only use the x values here. Only uses the x values. So we see here, the graph is decreasing all the way down here to -1. It's decreasing. What's it doing from -1 to 3? It's constant. From -1 to 3. And then at 3 to 5, it's going up. And then from 5 to infinity, it's going down. So that's what we're looking at there. So where's the function decreasing? Where is it increasing? And where is it constant?
Is decreasing from -5.
From -5, be over here somewhere. We only use the x values. So where is it decreasing? Where's the graph going down? No. It's decreasing from -3 to 3. That's the only place where it's going down. From -3 to 3. Remember, use your pen. Is it going up or down? That's going up. That's going down. And that's going up. So where is it increasing? It's increasing from -infinity to -3. Because the graph here, even though this arrow's pointing down here, we read left to right. The graph is going up to -3. Then it starts going up again from 3 to positive infinity. Is it constant anywhere? No, nowhere. So don't worry about what all these arrows mean at the end is the graph goes on infinitely from there. It doesn't mean that this is decreasing because you read left to right. As you go left to right, the values are getting higher and higher and higher and higher. So therefore it's increasing. It'll take practice for sure. Now, these type of questions, like especially this one here, we have a graph. We know it's increasing, decreasing now. Whenever you have sections that are increasing, decreasing, what you will have are, well, they're called extrema. Extremus Latin for the extreme values. What that means, it tells us what is the highest and what is the lowest. In other words, highest and lowest. Yeah, but we're dealing with Latin here. So it's what's the Latin word for highest or largest or biggest? Maximum. Or if you want to do plural, that's the plural value, maxima. Max means the most, the highest. The lowest, minimum, or in the plural is that minimum. So do we have in our graph here, do we have a maximum or a minimum?
Wouldn't maximum be infinity?
Very good. I'm glad you said that. Because the graph goes on forever. We have no absolute or no minimum because the graph keeps on going. What we do have, because it's only the small area here, this is a maximum because it's the highest of that point. It's what's called a relative maximum. It's relative to a small domain. So that point there is called a relative maxima. And this is the lowest point here, so it's called a relative minimum. So we have a relative max or a relative min. And you can have multiples of those. And then we can also talk about an absolute max or an absolute min. So what's the difference between the relative and absolute? The whole picture, right? The absolutes are maximum minimums, the highest or lowest of the entire picture. The relative is only just a small section.
So the graph over there has the absolute max is,
It doesn't have an absolute because it's arrows. If these were dots, then we can say those are absolute because they're higher and lower than everything else. That, yeah, let's look at that. So if I gave you the graph, that -7, -5, -3, 1, 3, 5. So this point here is at -5, 1. This one here is at -3, -1. This point here is 1, 1, 3, 1. This one's at -7, -4. So let's see if we have these values. Do we have a relative maxima? No. We do. Relative, remember, relative is only just a small area, a small domain of that graph. So are there any high points? So we have a point at -5, 1. That's a relative maximum. We have one at 1, 1. That's a relative maximum. And we have one at 5, 7. The absolute maximum can also be a relative maximum. Because remember, I said only of a small interval. That's the maximum of that small interval. Do we have an absolute maximum? At 5, 7.
The highest of the whole graph.
The highest of the whole graph, right? And the highest of the whole graph could be also a relative minimum because I can look at just a small interval. What's the relative minimum? We have -7, -4, -3, -1,
And 3 and
and 3, 1. What's the absolute minimum? Right. So that's what we're looking at. Maxima simply means the highest point. Minima means the lowest point. The difference between relative and absolute, relative is simply just the small interval. Absolute means the whole thing. Example 2. Given a function 0.1 x cubed minus 0.6 x squared, 0.1 x plus 2. It says, find any relative maximum minima and tell me where it's increasing, decreasing. Now, well, I want you, before you look at the picture of on the sheet, look at this function. What do we know for sure? There's two things we know automatically.
Since it has, exponent, let's see,
The highest exponent is called a degree. That tells us how many x-intercepts we can have. So since it's 3, the graph can look something like that. And since it's positive, since this is positive, we know it's an increasing function.
that would also tell us if it's a linear, or not linear.
Well, yeah, since it's 3, it can't be linear because the linear only has x, no exponent. And it also tells us, what's that tell us? The y-intercept. We know the y-intercept is at 2. So we'll graph these kind of equations in chapter 4. But now, for now, it's given to you. So it tells us that our point here is at -0.082, comma 2.004. That's the maximum. This point down here is at 4.082, comma -1.604.
Look at the coordinate graph.
A what?
The coordinate, they use some graphs for coordinates.
Yeah, all graphs are coordinates. All these points. The reason it's called coordinate because the x-axis is called the abscissa or ordinate, and the y-axis is called the abscissa. So since this is the ordinate, this is the coordinate. It's with they go together. So our relative minima is at this point. That's our relative minima. Is at here. Our relative maxima is at that point. Do we have an absolute minima, absolute maxima? No, because the arrow is going forever. So where is it increasing and where is it decreasing?
It's increasing from negative infinity.
And that's for our case, we'll put this in -3.
Oh.
We'll put this one as 1 and put this one as an 8. So where is it increasing? Where is it decreasing? Nope. I put these in there just to trick you.
It's still negative infinity.
Yeah, the graph goes on to negative infinity. So it's increasing from negative infinity all the way up to that point there. What's the x value of that point? Negative 0.082. That's where it's increasing. Is it increasing anywhere else?
Yeah.
Where? Yeah, from this point, 4.082 to positive infinity. And it's decreasing from this point to that point. From negative 0.082 to 4.082. There's no horizontal line anywhere. Okay, let's look at example 3. Oh, yeah. We can't do example 3 because I first have to define piecewise defined functions. A piecewise defined function is just that. It's a function that is defined by different pieces. So let's look at this. We have x plus 1. We use this function when x is less than -2. We use this function when x is between -2 and 3. And we use this function when x is strictly greater than 3. This is, so it's one function. It's got 3 parts, depending on where you are on the x-axis. Let's see how we would graph this. Okay, so for the first part, we look at over here. -2. Because if the x value is less than -2, I have to use this function. So because I can go all the way up there, what would my function be if I had x is equal -2? So -2 plus 1 is what? So at -2, it would be -1. So at -2, it's -1, but I can't use it there, so I have an open circle. Because it's not equal to. I can't use it. I can go all the way up to it. When x is -3, what is this equal? -2. When x is -4, the answer is -3. And so my graph on this part looks like this. So far, so good. Now, on the same graph, I go to the next set. I'm going from -2 to +3. So I'm going from this to this. Now, these are equal to, which means I can use -2. When x is -2, what's my equation? 5. So at -2 to 5, I got a dot at 5. At -1, it's also 5. At 0, it's 5. At 1, 2, and 3, it's 5. So it's a horizontal line. Because it's a constant function. And I have dots at both ends because I have the equality signs. So I have a solid dot at both ends. Now the third equation, for everything greater than 3, I use this function, x squared. So I start at 3, go to 4, go to 5. So what is 3 squared? 9. 4 squared is 16, 25. So when x is 3, 6, 7, 8, 9. I start off at 9 with an open circle, and then I keep on going up from there. That's what the graph's going to look like. So this tells me my domain, which x's I can use. And depending on which x's I can use, these are my functions. Let's do example 5 again. The same equations. X plus 1, 5, x squared. This is when x is less than -2, from -2 to +3, and when x is strictly greater than 3. Tell me the answers. What is this first one telling us? Yeah, so remember, these are functions. So whatever's inside the parentheses are my x values. So what is my function when x is -5? Now I gotta go over here. Which one of these satisfies -5? The first one, because x is less than -2. So I use this equation. -5 plus 1 equals -4. Since Kiara traveled at 35 miles an hour and Matthias is 40 miles an hour, and they start off at a right angle from the same hospital, that's Kiara's distance and that's Matthias' distance. The distance we're looking for is that length between the two cars. If we look at this graph, turn it sideways, what we have here is a right triangle. A squared plus B squared equals C squared. So A squared is Kiara's speed, we square it, and we add Matthias's speed, square it, square root both sides, and this is the distance between the two functions, between the two cars. The domain of this is inside a square root, you can only have 0. And since it can never be negative, t can be anything. So as long as you keep on going to infinity, you're doing good. Example 4. Community college, 30 feet of dividers set off in a rectangular area for students. Testing center, corner of the math lab is used as testing center. The partition, only 2 sides are needed. Express the floor area as a function of the partition length. Find the domain and use the graph below to determine the maximum area of the floor. We have our office space set off on one side of the math center. Since we're looking for the area, we have to use the formula base times width. Since we have 30 feet of material to deal with, all we know is that if the base uses X amount, then the width has to use whatever's left. So 30 minus X. So the base is X, the width is 30. Multiply those together, we get 30X minus X squared. That's our formula for the area. To find out what our values are, we set it equal to 0 to find our domain. We can factor out the X out of that, set them both equal 0. Because they're multiplied and they equal 0, we use a zero product principle, saying that the product of two terms, if they equal 0, that means the first term or the second term, or they're both equal 0. So X is 0, X minus 30 minus X equals 0. So this is my domain. So I'm going from 0 to 30. This graph is an upside down parabola. The highest is halfway through there at 15,255 or 225. So this tells us, since our size of our width of our box, the base is 15 feet, it'll give us the biggest area. So if the base is 15 feet, that means the width is 30 minus 15 is also 15. So it's 15 by 15. That's the maximum size. Oh, sorry about that. Let's go to number 6 now. Number 6, we're back to piecewise defined functions. Graph the function defined by this. 1/3 x plus 3 whenever x is less than 3, or negative x whenever x is greater than or equal to 3. G of x equals 1/3 x plus 3 whenever x is less than 3, then negative x whenever x is greater than or equal to 3. All right, so here's 3. Let's look at to the left of it. Let's look at all the values for x being less than 3. And we use this equation. So we'll start off with 3. And x is less than, so we go down. We go down to 2, to 1, to 0. When x is 3, and you plug it in there, we get 1/3 times 3. The 3's cancel, so we get 1 plus 3 equals 4. So at 3, we go up to 4. It's an open circle because I cannot use the 3. Well, we see this as a line, an equation of a line. So when x is 0, we get 3. So the graph on this side looks like this. Because this is a linear equation for everything less than 3. We just need 2 points. Whenever x is greater than 3 or equal to 3, we use this function. So we use from 3, 4, 5. When x is 3, y is negative 3. When x is 4, it's negative 4. When x is 3, y is negative 3. It's a solid dot because I can use 3. When x is 4, and it's linear, so it looks like that. Again, you should practice doing these instead of looking at the answer I gave you here. Because you'll be doing this yourself on the homeworks. But this is how you do it. You have to, that's the reason we spent chapter 1 learning how to draw equations of lines. But with piecewise defined functions, we have multiple graphs on the same graph. Example 7. F of x equals 4 when x is less than or equal to 0. 4 minus x squared whenever it's 0 to 2. 2x minus 6 whenever x is strictly greater than 2. So the first set, I start off at where? And go which direction?
So it's 0.
Start at 0 and go which direction? What does it tell me? How would you read that? X is what?
Is less than or equal to 0.
Yeah, so I'm going from 0 to the left. It's less than. All those, that means makes it x is equal to 4. y is equal to 4. So when x is 0, y is 4. When x is -1, y is 4. When x is -2, so from here on out, it goes on to infinity. It's a horizontal line. Okay, for this next one, we're going between 0 and 2. So from 0 to 2, when x is 0, we get 4. When x is 1, 4 minus 1 is 3. And when x is 2, we get 0. So when x is 0, it's 4. And that's an open circle there. So it's already taken. When x is 1, it's 3. And when x is 2, it's 0. So since it's a quadratic, it's a curve. Not a straight line, it's a curve. Because it's a quadratic equation. In this last one, I go from x is greater than 2, which I start off at 2, 3, 4. And I use this equation, 2x minus 6. So 2 times 2 is 4, minus 6 is -2. 2 times 3 is 6, minus 6 is 0. 8 minus 6 is 2. I cannot use 2, so it's an open circle there. At 3, it's 0. And at 4, it's 2. It's a linear equation, so it looks like that. So that's what we're trying to find there. Yeah, we'll skip 8. It's gonna be the same thing, but I don't want to deal with. Well, let's look at 8. It's a bit, yeah, we'll do it. Example 8. F of x equals x squared minus 4 over x plus 2. This is when x does not equal -2, and this is when x equals -2. The reason why I was thinking about skipping this one, because again, we don't talk about this stuff until the next chapter. Look at the top equation. Believe it or not, that graph is a straight line. Because x squared minus 4 over x plus 2 can be simplified. We're going to learn that x squared minus 4 can be broken down to x plus 2, x minus 2. Again, that comes next chapter, but they threw it here for some ridiculous reason. We see that the x plus 2's cancel. So the equation of our graph is x minus 2. We know when x equals -2, the answer is +3. And this graph of the top line is x minus 2. It's a linear equation. The y-intercept is at -2. The slope is 1/1. So it looks like this. Because at -2, if we plug it in there, we get -2 minus 2, we get -4. But since I canceled that, I have to have a hole there. I have to have a hole there because I removed one of those. Okay. So again, we haven't talked about factoring yet, but yet to do it in there. This is what to look forward to. The last part of this section is what's called the greatest integer function. Tomorrow we'll start off by talking about the library of functions, because we have a whole bunch of these functions we're talking about, but we never define them all. So tomorrow we'll do that. The greatest integer function, the formula looks like this. It's a bracket with a line inside there. What the greatest integer function means is no decimals. So what does that mean? At 0, the answer is 0. Let's say we go at 0.5. If you have 0.5 right there, cut off the decimal, what are you left with? 0. If you have 0.9, what do you have? 0. So all of these are 0 until you get to 1.0. So what happens at 1.0? It becomes 1. So at 1, it jumps up to 1. So that means we have an open circle down there. And the same thing happens there until we get to 2. Then same thing happens till we get to 3. And the same thing happens on the negative side. So what the greatest integer function does, it just truncates all your decimals. You have no decimals. That's the graph. And it keeps on going forever and ever. So what's the domain? And what's the range of this function? Are there any x's that are skipped that aren't being used? No, because all the X's are used. If it goes from here, it jumps up to there. I still use this number. I go to 0, I jump up. So the domain is from negative infinity to positive infinity, or all real numbers. What's that? Nope, because the range are the Y values. Nope, we don't have decimals. We can use all the decimals inside there, but we don't have decimals on the range. The range are only integers. And that's it for that section. You really don't see those too often anywhere, but we had to throw it in there just to show you what it looks like. Yeah, I was thinking about starting section 2, which deals with algebra of functions, but we'll do that next time. Yeah, we'll probably finish up the chapter next time because it's all pretty short and sweet. We have the algebra of functions, how to add, subtract, multiply, divide functions. Then we have symmetry, talk about odd, even functions and reflections, and we do transformations. And that one will take the most time. So we'll be in good shape because next week we'll definitely start chapter 3. Okay, everybody, have a great, safe day. I'll